Algebra 2, Chapter 5, Section 3, Solving Linear Equations. Let's go ahead and start by doing an example of solving a linear equation. So a linear equation is just an equation where we have two linear expressions equal. So just like it says in the name, linear equation. So if we have one linear equation, 3x plus 7, and we set that equal to some other linear equation, 7x plus 3, we want to be able to solve this kind of equation. So let's do an example. Incandescent light bulbs are cheaper to buy, but more expensive to operate because they are less efficient than fluorescent light bulbs. The total cost in dollars to purchase a bulb and operate it for T hours is given by the following functions, where F is for the incandescent, which these days we can still buy incandescents, but they're called a halogen. They're just incandescents with halogen gas, which makes them a little more efficient and a little more expensive than the old incandescents. And fluorescent bulbs. And now we have a third category of bulbs that are common around, which is LED. This problem predates that. So fluorescent bulbs are cheaper to operate, slope is lower, but they're more expensive to purchase. So A, how many hours of operation gives the same cost with either choice of bulb? So that would mean when is the output of F equal to the output of G? And we can figure this out by setting the rules equal to each other. 0.5 plus 0.004 T equals 5 plus 0.001 T. All we have to do is gather like terms. So subtracting 0.001, we get 0.003 T, or 3 thousandths. And 5 minus 0.5 gives us 4.5. So T must be 4.5 over 0.003, which we could do with some time, but why don't we go ahead and use a calculator to find that. 4.5 divided by 0.003 is 1,500. 1,500 hours. The answer to part A. Part B, graph the two functions and indicate in each region where the function is cheaper. Well, let's use some graph paper. Let's make a new graph page here. Let's turn it into a graph page, sorry. Hold on. Here we go. So we have a graph. In this case, time isn't going to be negative. We can't operate negative hours. And the cost is never negative in this particular problem. It's always going to be positive. So we're going to have time going this way. And we're going to have cost going this way, up. Horizontal. Sorry, vertical. Up is vertical. Horizontal goes left and right. So this is the cost to operate. Okay. One, two, three, four, 5. 1, 2, 3, 4, 5, 10. Okay, and if we go back and look at our hours, 1,500 hours is when we broke even. So let's go to 2,000 hours. So we have 5, 10, 15, 20. So this would be 1,000, 500, 1,500, 2,000. Time is in hours. The cost is in dollars. Okay. Now the first function, F, was 0.5 plus 0.004. Okay. So we have 0.5. So F starts here at 0.5, or 1/2. And it has a slope of 0.004, which is 4 thousandths. Now we have our 1,000 here, so at 1,000 run with a slope of 0.004, we should rise 4 units. Okay, so that means we'll rise 4 units to 4.5. here, and in 500 units we should rise 2 units. So 1500 we should go up 2, and at 2000 we should go up another 2, come over. Okay, now let's draw F in blue. So we draw our line. Might be nice to use a ruler to get a nice straight line. In fact, maybe we can figure out how to do that real quick here. I use a ruler to do my line. Get a nice straight line. Okay. In blue. And this is, blue is F of T, which F represented incandescence. Fluorescence was 5 plus 0.001. So we spend $5 at the beginning, but our slope is 0.001, meaning in 1,000 units we're only going to rise $1. $1 every 1,000 hours to operate. Okay, we'll draw this line in red using a ruler. So we have a nice straight line. And we see that the graphs cross right here at 1500, which is what we expect. The output of F and the output of G is the same at an input of 1500. So we've done the graphing, but the question also says indicate in each region which function is cheaper. So we have a few regions here. Let's draw a little dashed line here at 1500 going up, indicating the break-even point. Okay, so at this point, the functions have the same output. So in this region here, the function f is cheaper. This is cheaper. Okay, f represents the incandescent bulbs. So in this region, the incandescent, how do we spell that? D-E-S, like descent. Incandescent bulbs are cheaper. After 1500, the fluorescent bulbs are cheaper in this region here. Right? In this region, the fluorescent is cheaper because at this point, and I overdrew, I went past red, so we need to erase this. Yeah, let's just go back. So don't go over the red line between the origin and here. So all this space here, the fluorescent was cheaper. Okay. These days you might be able to buy an LED bulb for $7.50 that is even cheaper to operate over time. So there's another set of equations we could write if we wanted to analyze all of the light bulbs in the market today for their cost versus time. Solving linear equations going on. Let's solve some just algebraic equations here to show some of the other cases that might come up. Let's do A. 3x plus 5 equals 3 times x plus 5. Gives us 3x plus 3 times 5 is 15. If we subtract 3x from both sides, we're just left with 5 equals 15. Huh? So what this means is no such x. There's no value of x that makes this equation true. Nothing I put in will ever make 5 be 15. Okay, so there's no answer, no solution. B. 3x plus 5 equals this 3 times the quantity x plus 1, distributing, plus 2. We get 3x plus 3 plus 2. Subtracting 3x from both sides, we end up with 5 is 3 plus 2. We end up with 5 equals 5. Huh? This is always true. 5 is always equal to 5. So any x is a solution, which we can write then also the way infinitely many. I can't remember if there's an E here for infinitely. Let me look that up real quick so that we make sure we spell everything right. But there are infinitely many solutions. Any value of x that we put in will give us an output. Give us a true statement, true equation. And yes, there's an E here. Infinitely many solutions. Now, so we've just seen the very first thing we did. There was one solution when the light bulbs were equal in terms of their cost. We just saw examples where there were no solutions and where there was infinitely many solutions, or any value of the variable makes the equation true. And if we think of the graph in each of these cases of the line, in the case where there's one solution, if we have two lines, we'll have one line going this way, and we'll have a second line going some other way. And where those lines cross, where they intersect, is the one solution. If there are no solutions, then the line, if we draw our graphing lines here, our axes, if there are no solutions, we have a line, and then we have another line that's parallel to this line, which means they never touch, they never intersect. This represents the case of no solution. And the third case we have is we have a set of axes, we have a line, and then we have another line, and we want to know where these are equal. But this other line, the red line that I'm going to draw, is exactly on top of the blue line. And so all values of the variables yield intersections. So there's infinitely many, which I'm just going to abbreviate like this. Infinitely many solutions. So the number of solutions is infinite. So let's use what we've learned and do a few more examples. So suppose we pay a total of $16,368 for a car. But the list price, the price before we have to pay any taxes, is this unknown dollars of P dollars. So we want to find the list price, this P, find the list price if you buy it in A, Arizona. Arizona has a sales tax of 5.6%. So if we have the list price, P, we have to add this tax, 5.6%, which means per 100. We can write as 0.056 by pushing the decimal over 2 times the list price equals the price we paid, $16,368. So adding the coefficients of P, in other words, factoring P out, we get 1 plus 0.056, so we have 1.056P equals 16,368. Now we can solve for P by dividing both sides by 1.056. So we would have 16,368 divided by 1.056 and get $15,500 was the list price. Okay. B, New York, which has a sales tax of 8.25%. Well, the logic we used to set up A is the same for B, just the number is different here. So we'll just write directly what we would have gotten if we had 0.0825 here. 1.0825P is 16,368. So pulling our calculator back up, 16368 divided by 1.0825, $15,120.55. $15,150.55. cents. Make sure I got that right. Okay, so that was the list price of the car in New York for us to pay the same final price since it has more tax. C, an arbitrary state with sales tax rate of R. So here the rate is R. The rate is what we put in here. We took the percent and we turned it into just a rate, a number we can multiply by. So we would have 1 plus the rate times P equals the final price, 16,368. And so all we need to do to find the abstract answer is that the price in dollars is 16,368 divided by 1 plus the rate, R. Different example. If P dollars is invested at an annual interest rate, R, compounded monthly, then its value in dollars after T years is P times the quantity, 1 plus R over 12 to the 12T power. What amount, and sorry for the misspelling here, what amount must be invested to produce a balance of $10,000 after T years? Okay, we've got to unpack this. This is very complicated. So P is dollars. Okay, so we put dollars into an investment. Every year, we get out an annual rate. Annual means year, right? And it's compounded monthly, and we're given it this value for the compounded value. Okay, so T is years, so here P is our sort of our initial value, what we stuck in. T is our input, in this case our variable. It's years, okay? It's after T years. R is just some constant, okay? It's some rate that we're going to get for a particular investment. It's not our variable in this case. Our variable is T. So P is the money we put in. R is our rate, okay? A balance of $10,000 after T years. Okay, so what we're wanting to know, I'm sorry, I got this wrong. So the input is the amount we're trying to invest, right? We're trying to figure out what amount do we need to invest after some unknown T years. So if T were 10, we would write the value of 10 up here in this exponent, okay? So there's two constants. There's T and there's R. Because what we want to find is P, the amount that we need to invest. Okay? So we want to know how much do we need to invest to get out $10,000 at the end of these T years. Okay, so the rate is a constant. The number of years it's invested is a constant, even though it's abstract. And the rate's a constant, even though it's abstract. What we want to do is solve for P, okay? So that we have P in terms of these other abstract constants. So how can we do that? Well, we just need to think, if we think about these as numbers, if T were 1 and R were 1, we'd have 1 plus 1/12 to the 12th power, which we could find with our calculator and divide 10,000 by. So we can just leave this whole part of the expression over here as an abstract thing. Okay, so we write the equation, 10,000 is P, 1 plus R over 12 to the 12T power. But R and T are just constants. All we need to do is find P. So we just need to divide by this number. So P is 10,000 over 1 plus R over 12. Oh, no. Be careful here. We don't group the 10,000 with the exponent. It was not part of that number. To the 12T power. Okay, and that has to all happen first. So we put it all under the bar.